In this lecture video, we are going to take a look at calculations that involve with chemical equilibrium. Please read the OER textbook chapter section 13.4 for more detail. The calculation that involves with equilibrium is going to focus on the concentration of the substance within the chemical reaction. So for example, we'll look at the initial concentration of our reactant and product. And also we are going to take a look at the concentration that change as well during the reaction and also the concentration at equilibrium. First, let's take a look at the change in concentration of the reactant and product first. Okay, so in this case, we are going to tie this back into the stoichiometry because everything when it's changed is going to be according to the stoichiometry within the chemical reaction. Okay, so but before we start, I'm going to give you the condition where we have Q less than K. Whenever that the reaction quotient Q is less than equilibrium constant K, is indicate that at this point is not at equilibrium yet. So the reaction is going to shift. Okay, so it's indicated at this point we have more of the reactant than the product. So it's going to shift toward the product to make more of the product. Okay, so let's see. We are going to take a look at the change of this chemical equation right here. Okay, so this chemical equation is involved with 2 mole of ammonia that is going to decompose into nitrogen gas and hydrogen gas. Okay, 3 mole of hydrogen gas. So according to this, right, if you looking at the change, because we have more of the reactant, therefore, over time, the reactant is going to decrease by how much, right? So it's going to decrease by 2 mole, right? Per 1 mole of this, per 3 mole of this. So that means in this case, if you want to look at the change, you are going to see the negative change of the reactant and you are going to observe the positive change for the product, okay, in the ratio according to the coefficient. Okay, so note that in your lecture manual, there is the shift of the amount. So can you actually move so that it's actually aligned with those species? Okay, so in this case, we will see that every 2 mole of ammonia that is depleted is going to produce 1 mole of nitrogen and 3 mole of hydrogen. Okay, so the reason why I use X because right now the change can be anything, right? It doesn't have to be 2 mole exact, right? So in this case, it's going to be just the ratio that we are looking at. Okay, so it's 2 to 1 to 3. Okay, so and again, X can be anything. Okay, so it's the amount of the change that happened. Okay, so the second scenario is happen when you have Q greater than K, right? So whenever the reaction quotient is greater than equilibrium constant, it's indicated at this point it's not at equilibrium yet. Therefore, that would be the shift, right? So at this point, we have more of the product than the reactant. So the reaction is going to shift in order to produce more of the reactant. Therefore, if you're looking at the change here, you are going to see that because product need to decrease, therefore, the product is going to have a negative change, right? And then the reactant would be a positive change because product need to decrease in order to produce more of the reactant. Okay, so that means in this case, in order to do the calculation that involve with change, you need to look at the Q first. Okay, so whenever the Q is less or greater than K, that is going to indicate whether the change is going to be negative or positive. Okay, so we can use this idea later on. Now let's take a look at example 1. Okay, so example 1, we are going to looking at the change of the concentration X. Okay, so we don't know how much X is, but we are going to looking at the X with the ratio of the chemical equation. Okay, so let's take a look at 1. Okay, so 1A. Okay, so in this case, it tells us that this is the reactant and this X is positive, right? So if the X is positive, it indicates that the second reactant is also going to be a positive X as well, right? So it's implied that if this is positive, this one have to also be positive because it's also the reactant. So that means in this case, it's implied that the product need to be negative. Okay, so the reason for that is because if you have a positive reactant, where it's going to come from? Well, it's going to come from the product, right? It's going to be produced from the product in this case, but it's going to be produced from the reverse direction. Okay, so that means in this case, the change of this equation A is going to be plus 2x for bromine and then negative x for the product. Now let's take a look at B. Okay, so in this case, we have product as a positive x. So this means it indicates that the x is being produced, right? So the product is being produced over time, right, in order to achieve the equilibrium. Therefore, the product is going to come from the reactant. So in this case, the concentration of the reactant need to be negative, but it need to deplete over time. So therefore, since the ratio is 1 to 1 to 1, so therefore the first 2 reactant is going to decrease by negative x and negative x. Okay, so again, these are omit as 1. Okay, so there's the number 1 in front of this. Okay, so don't forget that. So C, okay, so we have positive change in reactant. Therefore, the change for the product would be negative, right? So that means in this case, the answer should be +5 for the second reactant and -3 for the first product and -4 for the second product. Okay, now for D, okay, so what happened then if there is nothing given to us? So in this case, if nothing given to us, we are going to assume that over time, you are going to have the reactant to decrease, right? Because over time, let's assume that we're always going to start with the reactant. So in this case, the reactant would be negative, okay? And then the product would be positive change. Again, the changes in concentration here is going to follow the stoichiometry between each species within the chemical equation. So this is just one puzzle in a big picture. Okay, so when you are looking at the calculation involved with the concentration in equilibrium, you are going to take a look at the change. Not only that, you are going to take a look at the initial and also equilibrium concentration as well. In order to calculate for the initial and the concentration at equilibrium, you are going to use Rice table. Okay, so R stands for reaction, I stand for initial, C stand for change, which what we just saw. Okay, so in the previous slide. And then E stand for equilibrium. So all of these are going to related to the concentration at each of these points. Please note that in the OER textbook, you are going to see the word ICE table instead of Rice table. The reason why I need to use Rice table because I just want to emphasize that you need to include with the reaction. Okay, so you need to include with the chemical reaction or chemical equation. So that way it's easier for you to follow what is going on. Another thing that I want to point out is that when you filled in the Rice table, you need to use molarity unit, which is mole of solute, right, equal to liter of the solution. Okay, so you need to know how to convert these units now. Now let's take a look at example 1. Okay, so example 1 asks us to calculate molarity of these two species at equilibrium. Okay, so it's giving us the Kc value. Okay, so again, what I would like you to do is set up the Rice table because it's always going to be clear and you will not make mistake if you set up the Rice table. So what is the Rice table again? So as I mentioned, right, you need to start with reaction. Right? So this is the chemical reaction because chemical reaction will tell you what is the ratio. Okay, so then we are going to start with initial. So initial stands for initial concentration. Okay, so we have change and we have concentration at equilibrium. Okay, so this is the change that we see from the previous slide, which is the ratio according to the coefficient for each of those species within. Now let's take a look at how can we fill into this table. Okay, so if you think about this, when we looking at how to express Kc or the equilibrium constant, we know that we will exclude the solid and liquid, right? So in this case, you can exclude those solid. Okay, so we are going to include only gas and aqueous in this case. Okay, so that means in this case, the Kc expression will not include solid. So that means I can ignore the solid. Now, the next thing is this problem doesn't give us anything else but Kc value. So that means we are going to assume that at the beginning, we are going to have 0 concentration of the product, right? So let's say like, let's assume that before, at the beginning, we don't have any product at all. Okay, so now the change, right? So change would be the positive change in this case, because over time, right, the product is going to increase over time. So therefore you are going to get the positive X for the change. Again, we don't know what is the change. So I'm going to use X in this case, molar. Okay, so these are the units, right, for each of these concentration. Okay, now what would be the equilibrium then? The equilibrium would be when you add these two together. Okay, so the equilibrium would be when you add initial and change together. So equilibrium of these two species would be X molar. Okay, this equilibrium right here, this concentration is going to be the concentration at equilibrium. It's going to be concentration that you can use to calculate for Kc. So therefore, what you can do is you can write out Kc expression. So Kc expression of this again is going to be product, right? So multiply by each other and divide by the reactant. But since the reactant is solid, so therefore it's going to divide by 1, right? So in this case, just equal to itself. So that means in this case, the Kc value right here that we are given, you can plug that in, right? Because we already know the value of it. And this concentration here is have to be concentration at equilibrium. Remember, the Kc is equilibrium concentration. So the concentration have to be at equilibrium. Therefore, in this case, you can plug all those unknown value in, right? So which is going to be that 2x. So therefore, in this case, you are going to get x squared, right? So in order to find out x, you are going to do square root of that. You are going to get x equal to this number right here. Okay, so therefore, in this case, since x is equal to the concentration at equilibrium of these two species. Therefore, we can say that the concentration at equilibrium for ammonia and for hydrogen sulfide is going to equal to 1.1 times 10 to negative 2 molar. Okay, so don't forget the unit. All right, so let's take a look at 2. Okay, so in this case, I would like you to pause the video and try to complete this on your own and resume the video again after you finish. All right, let's check your work together. Okay, so in this problem, again, it's asking us to find out equilibrium constant. So this is going to be K, right? So that means we need to know the concentration of each of these species at equilibrium in order to find out the K value. So that means we need to set up the Rice table. Okay, so the Rice table, the reaction is already given. So it's going to be this reaction right here. So therefore, in this case, I'm going to extract the information in order to fill into this table. Okay, so it tells us that the initial concentration of each of these species. Okay, so of each of these species is given as this molar. Okay, so I'm going to fill those in. Okay, so in this case, we are going to start with the concentration of the reactant. It doesn't tell anything about the product. Therefore, we are going to assume that the product at the beginning, right? So since we are not given the concentration of the product at the beginning, so it's going to be equal to 0. Okay, so again, the reason why it's 0 because at the beginning, there is no product yet. Okay, so and also the problem doesn't tell us about the concentration of the product as well. So that means we are going to assume that at the beginning, concentration of product will equal to 0. Now let's take a look at the change. Okay, so according to what we learned in the previous slide, okay, so we know that the change of the reactant is going to decrease over time in order to produce product. So therefore, in this case, the change of the first and second reactant is going to be a negative X. I don't know yet how much that is. Okay, so it's going to be negative X. And then the change of the product would be positive X because over time the product would be increased. Now for the equilibrium, okay, so you are going to add these two together. Okay, so what you are going to obtain is going to be 0.001 minus X for the first and second reactant. And then the product would be X molar. The next information given from the problem would be the concentration of iodine, right? So this one right here at equilibrium. Okay, so it tells us that this is going to be the concentration of iodine at equilibrium, which is going to be this value right here. Right? So this is the concentration at equilibrium. So that means these two values are going to be identical. Okay. So if you're looking at this, right, so the concentration at equilibrium of iodine is going to be the same as concentration of iodine minus. So therefore, we can also say that as well that the iodine minus is going to have the same concentration of neutral iodine. Okay. Now to find out X or the concentration of I3 minus, you would need to solve for it, right? So since we know that this concentration right here is equal to this given value, therefore, all you need to do is you just need to set it up, right? So equal to each other and then solve for X. So therefore, X is going to come out to be this value right here. So that means the concentration of I3 minus is going to equal to this molar. So since you know all of those concentrations, the next thing you are going to do is to write out Kc expression. Okay, so the Kc expression is going to be product over reactant. And since we are looking at the equilibrium constant, therefore, each of these concentration have to be the concentration at equilibrium. So it's going to be concentration at this point right here. So that means we already know that them, right? So you just need to plug all of them in. Okay, so and then solve for Kc. Remember, Kc doesn't have any unit. Okay, so the equilibrium constant doesn't have units. So you just leave it as unitless. For the previous two problems, you see that only the concentration of the reactant is given at the beginning, right? So in this case, we are going to take a look at the example where you are going to be given both reactant and the product. So in this case, we need to determine how the change would occur, right? Whether the product is going to decrease or the reactant is going to decrease, right? So we are going to take a look at the Q value in order to help us to indicate the direction of the change. Okay, so this problem right here asks us to find out the equilibrium concentration, okay, of those species. Okay, so it's giving us the Kc value. Okay, so again, whenever that you looking at the equilibrium concentration, you are given the equilibrium constant, we are going to use Rice table. So I'm going to set up Rice table. Okay. So what I'm going to do next is that I'm going to cross out all the solid. The reason for that is because in this case, solid would not be included in the Kc expression. Okay, and we are going to start the concentration of oxygen with 2.2 molar. Okay, so we are going to start with 5.5 molar of sulfur dioxide. Okay, so again, the concentration have to be in the unit of molar. The next thing is to determine the change. Okay, so as we learned at the beginning of this lecture video is that in order to find out the change, you need to know the Q, right? So because the Q will tell you whether the reaction will shift left or right. So I'm going to go ahead, find out Q first. Q mean that we want to know if this condition that is given is already at equilibrium or not, right? So this is going to be the Q value that we are going to take a look at. Okay, so in order to find Q, we are going to use concentration of the product over reactant. Okay, so in this case, the value that is given would be these two. Okay, so we're gonna find out at this point whether it's already at equilibrium or not. Okay, so if you calculate for this, Q value come out to be 2.5, which is greater than K. When you have 2.5, which is greater than K, it tells us that at this point it's not at equilibrium yet. Okay, so that means the answer would not be 2.2 and 5.5 because it's not at equilibrium yet. So at this point, you have more of the product than the reactant. So in this case, the reaction will minimize the amount of the product, right, in order to establish the equilibrium. Therefore, in this case, the reaction would shift toward the reactant. So that means over time, the product would decrease, right? So I'm going to get a negative X. The reason why negative X, because we have one ratio here. And over time, the reactant would produce, right? So it's going to be positive X. So again, in this case, because both reactant and product are given, so you will need to find out Q in order to determine the direction of the reaction. Okay, so in this case, after you know the change, then the equilibrium would be the addition of those two, right? So the equilibrium concentration of sulfur dioxide would be 5.5 minus X, and concentration of oxygen would be 2.2 plus X. Okay, so now these are the concentration that we are looking at, right? So this is the concentration that we are looking at, asking us to find. Okay, so we're gonna find those. Okay, so go ahead, set up the Kc expression. So Kc expression would be, again, it's going to be concentration of product over reactant. Now you have to do next is plug everything into K. Okay, so K is given. Okay, so this concentration here are the concentration at equilibrium. Okay, it's gonna be these two concentrations. So plug those in. You are going to get 1.5 equal to 5.5 minus X, which is the concentration of sulfur dioxide, and then over 2.2 plus X, which is the concentration of oxygen at equilibrium. Okay, then all you need to do is solve for X. Next, you are going to distribute 1.5 into these parentheses here to get this. Next, you are going to move X to be on the same side. Okay, so I'm going to add positive X, and then you are going to then move number to be on the same side. Okay, so you are going to get 2.5x equal to 2.2. Then solve for x by divide both sides by 2.5. Okay, so this x is not the final answer. This x tell you about the change. Okay, so in order to find out the equilibrium concentration, what you need to do is that you are going to need to plug x back into the equilibrium concentration. So that means in this case, you are going to get concentration of oxygen at equilibrium equal to 2.2 plus 0.88. Okay, and that would be the answer. And then for sulfur dioxide, right, so SO2, you are going to get 5.5 minus 0.88, right? So that is going to equal to 4.62 molar. Please note that this is concentration, so therefore it should contain unit. So don't forget the unit for the concentration. All right, for the example 4, in this case, I would like you to use what you just learned from the previous example, and I want you to attempt this on your own. Okay, so if you are struggle with this, no worry, you can resume the video again when you're ready. Okay, so let's try your best first. All right, let's take your work together. Okay, so in this case, it's giving us the initial concentration of each of these species. Okay, so carbon, oxygen, and also carbon dioxide as well. So that means you are given all of it, right? So you are given both reactant and also product as well. Therefore, in this case, you will need to determine the Q first, right? So in order to find out which direction is going to shift. Okay, so again, whenever you are giving both concentration of the product and reactant, you need to find out Q first to determine the direction of the reaction. Okay, so in this case, what I'm going to exclude or the information that we will not need to use would be the concentration or the amount of grams of carbon. Again, the reason for that is because carbon is in solid state. So we can exclude that. Okay, the initial concentration for oxygen would be 3.8. Okay, so for carbon dioxide would be 1.5 molar. Okay, so now to find out the change, you need to set up Q. Right? So Q will be product over reactant. So plug in those values, you are going to get 0.39. 0.39 indicate that Q is less than K. So at this point, it's not at equilibrium yet. At this point, we have more of the reactant than the product. Okay, so therefore, in this case, the reaction would shift in order to minimize the reactant to produce more of the product. So it's going to shift toward the product. Okay, so that means the change for this would be the reactant would be a negative change and the product would be a positive change. Okay, so you are going to get the change equal to that. Okay, so the equilibrium concentration would be 3.8 minus X for oxygen and then 1.5 plus X for carbon dioxide. Okay, so now after that, you are going to set up the expression for Kc. Okay, so expression for Kc would be similar to Q, right? So product over reactant again, but in this case, you are going to use concentration at equilibrium. Okay, so don't forget that. Okay, so plug everything in, right? So it's given Kc value as well, so plug those in. The next thing is move this term to the other side. Okay, so you are going to multiply by 3.8 negative X for both, right? So in order to get rid of this. Okay, so what you are going to do next is distribute 13.8 into the parentheses. Okay, so you're going to get this one. The next is move X to be on the same side. Okay, so I'm going to add 13.8 to both sides. And then the next step would be moving the number to be the same side as well. Okay, so you are going to get this. And then you are going to divide both sides by 14.8 to get X. Okay, so again, X is not your final answer. X indicates the change. Okay, so therefore, in this case, in order to find out the concentration at equilibrium, you will need to plug this back in, right? So plug this back into the concentration at equilibrium. So therefore, the concentration of oxygen would be 0.4 molar at equilibrium, and also concentration of carbon dioxide would be 4.9 molar at equilibrium. Now let's take a look at example 5. Okay, so example 5 is giving us Kc. Okay, so it's tell us the initial concentration of the reactant, right? So that one, asking us to calculate the concentration at equilibrium again. Okay, so that means in this case, we are going to do the same thing, set up Rice table. Okay, so I'm going to set up Rice table. So Rice table, Rice stands for reactions, right? So the reaction is given. So is that reaction right there. Next is to fill out the table. Okay, so again, it needs to be in molar concentration. Okay, so the initial concentration of the reactant is 2.8, right? It's given. And it doesn't given anything about the product. Therefore, in this case, the product would be 0. Okay, so if the product is 0, you don't need to find out Q because you know exactly that the product is going to be increased by over time and the reactant would be decreased. On the other hand, if the product is given, but that it doesn't given any reactant at all, then you are going to assume that the reactant would be 0, and then the change would be the positive for the reactant and the negative for the product. Okay, so it's depend on what is given. So in this case, doesn't given the product, so the product would be 0. So again, the change would be negative 2x for the reactant because the reactant has coefficient 2. Okay, so and it's going to be positive 2x for the NO. Okay, and then positive 1x for the chlorine. Okay, so again, over time, since we have more of the reactant than the product, so over time the reactant would decrease. Okay, so equilibrium would be when you add these two together. Okay, so in this case, you are going to get 2.8 minus 2x, and then it would be 2x for, and x for the rest of those. Okay, so now the next thing is to find out the concentration at this point, right? So we want to know the concentration of NO and Cl2, right? At equilibrium, we want to know this concentration. Okay, so you are going to set up the same thing, right? So we are going to set up the K expression. Okay, so the product over reactant, don't forget the coefficient. Okay, so don't forget to square those. Okay, so that's the most common mistake. Okay, so the next thing would be add so it's this value for Kc that is given, right? And then these are the value for the concentration at equilibrium. Okay, so I'm going to add all of those. The next thing is to solve for x, right? So in this case, you see that this whole term is square. So that means all you need to do is that you need to pretty much solve for this and then set it up as quadratic equation, right? To solve for x. Okay, so using quadratic equation is a little bit complicated. So I'm going to teach you a simple way to solve for this. Okay, so by looking at the relative value of Kc. Okay, so the Kc value, as we learned in the previous lecture video, that Kc value tell us about the stability of the reactant versus the product, right? So the Kc that is given here is a very small value, right? A lot smaller than 1. Right? So this Kc right here is a lot smaller than 1. Is 0.00078. So when Kc a lot smaller than 1, it tells us that the reactant is more stable than the product. So that means majority of the species will stay as the reactant. It doesn't want to convert to the. So that means the change here is going to be very, very small change in comparison to the initial concentration. Okay, so that's why the Kc is very small, because it doesn't want to convert to the product at all, because product is more unstable than the reactant. That's what it tells us. So that means if I compare this value, if I compare negative 2x to 2.8, negative 2x is very, very small. That is actually negligible. Okay, so we are going to, again, in comparison to 2.8, this is negligible. It's similar to if you have $2.8 million. Okay, you lost $2. It doesn't matter, right? You lost $2 out of 2.8 million. So that means $2 in comparison to 2 million is negligible. Okay, does that make sense? However, these are not going to be negligible. The reason for that is because if you have $0, right, you gain $2. That is significant, right? You gain a significant amount of money, right? From $0 to $2. That is significant. So therefore, in this case, you are going to keep those the same. The only thing that we are going to ignore, it would be the negative 2x, because you are compared this with a lot of the reactant that doesn't want to convert much to the product. Okay, so in this case, because this value is negligible in comparison to 2.8, therefore, Kc, which is going to equal to everything the same, except instead of 2.8 minus 2x, now we're going to have just 2.8. Okay, so the reason for that, again, is because negative 2x in comparison to 2.8 is negligible. Okay, if you do this, it's going to make your life easier. You don't need to go through the quadratic equation. So the next thing is to pretty much distribute this square inside the parentheses, right? So you are going to get 4, right? So 2 square and then x square. So x square multiplied by x, you are going to get x cubed. Okay, so it will be 4 times x cubed. And then you are going to move this to the other side, right? So you are going to get this value right here, divide both sides by 4, and then do the cube root on both sides. You are going to get x equal to this value. And again, x is not your final answer, because x is just the change. So in order to find out the concentration of NO and Cl2, all you need to do is plug those in. Okay, so you are going to get the concentration of those two equal to 0.23 molar and 0.12 molar. So you might ask me, when can I ignore the change in comparison to the initial concentration? The answer is when you observe that the Kc is a lot less than 1. Okay, if you are not sure, you can also use this approximation to help you as well. Okay, so x is the change, I is the initial concentration. If you divide by the change value that you calculate, okay, divide by the initial value times 100. If it's less than 5%, we can assume that the change is going to be negligible in comparison to the initial concentration. Okay, if not, if it's come out greater than 5, then you are going to use the quadratic equation to solve for the x. Okay, so which is a little bit complicated. Okay, it's feasible, but it's just a little bit challenging. So please note that on the exam, okay, you do not need to set up quadratic equation. On the exam, you should be able to use the approximation that I just teach you earlier to solve for the x. Okay, so again, on the exam, there would be no quadratic equation. On the exam, you can assume, okay, you can use this approximation to help you to find out x. Okay, so that would be simpler. Now let's take a look at 6. Okay, so I would like you to pause the video and then attempt this on your own first. Okay, so after you finish, then resume the video again. Now let's check your work together. Okay, so we're gonna reuse Rice table again because it's involved with equilibrium. Okay, so reaction is given. Okay, so don't forget that all of these have to be in unit of molar. Okay, so if it's not in molar, you need to convert in molar first. Okay, so it said that before the reaction occur. Okay, so it's giving you the concentration of these two. Okay, so that means in this case, we are going to plug in those values, and it doesn't say anything about the product. Therefore, in this case, we're going to assume the product equal to 0. Okay, so that means in this case, the change of the product would be positive and the change of the reactant would be negative. Okay, and the equilibrium would be the summation of initial and change. All right, now we want to find out the concentration at equilibrium of oxygen, right? So that means in this case, we want to find out what this is. Okay, so I'm going to set up the K expression. Okay, so product over reactant. Don't forget the square, the product. Okay, so K is given is 1 times 10 to negative 5. Okay, so you are going to plug in all of this value at equilibrium to this Kc expression. Now to solve for this, you are going to pretty much multiply these two terms, right? And then set up quadratic equation to solve for x. but that is a little bit complex. So before we do that, we actually need to check value of Kc first in order to see if we can use approximation or not. Okay, so this Kc value given to us is a lot less than 1, right? So this value here is equal to 0.00001, right? So it's a lot less than 1. It means that the change is going to happen, very small change, but it doesn't want to change much at all. So majority of them still gonna stay as the reactant, right? Because as we see, right, Kc tell us the stability. So in this case, when Kc less than, it tell us that majority of them going to stay as the reactant. Now you can see that when we compare the change to the given initial concentration, okay, we can say that the change is going to be negligible. Okay, so again, as I mentioned earlier, right? So let's say if you have $1.6 million and you lost $1, that's just not going to be significant, right? So same thing, right? If you have 0.4 million, you lost only $1, that is not going to be significant. Okay. However, if you have $0 and you gain $2, of course, going to be significant in that case, right? So in this case, we are going to omit those negative X in comparison to the initial concentration. Okay. So in this case, you can set up the new K. Okay. So K would be so I'm going to distribute this into it, right? So it's going to be 2 squares, so which is going to give us 4x squared. Okay, and then it's going to divide by 1.6 times 0.4. Okay, so because we are going to neglect those negative X in comparison to the initial concentration. Okay, so now we can solve for X now. Okay, so solve for X, you are going to get X equal to 0.0013. Okay, so again, X is not the final answer. The problem asking us the concentration of oxygen. Okay, so I'm going to plug X back into the concentration. So in this case, if you're looking at the concentration of oxygen, okay, so 0.4 minus 0.001. So in this case, the concentration of oxygen at equilibrium would come out equal to 0.3987 molar, right? So you can see that the negative X, right, is very small compared to the original concentration of oxygen, right? So if you're looking at the number of sig-figs, right, so this is subtraction, so you go by the least number of decimal places. So we have 2 decimal places here, so therefore your answer would be 0.4. So it's pretty much the same as the initial concentration of oxygen. The reason for that is because the change of the X is very small. Okay. All right, so again, let me assure you, okay, so the approximation would work whenever that you see the change in comparison to the initial concentration. If you divide these two and then multiply by 100, if it's less than 5%, you are going to see that the approximation would work. Okay, so similar to example 5 and 6 that you see earlier. However, if the ratio between the change and the initial concentration is greater than 5%, that's when you will need to use the quadratic equation to help you solve for X. Okay, but let me assure you that the quadratic equation would not be included on the exam. Okay, you might see some quadratic equation on the Newton homework. In this lecture video, you learn how to use rice table and also how to set up rice table to find out the concentration of the species, right? Whether it's going to be at the initial, at the change, or at the equilibrium. Okay, so please start working on your homework chapter 13.4 as soon as possible.